Okay, Assalamualaikum dan salam sejahtera. Today we continue our discussion about boundary layer, and I would like to focus in turbulent boundary layer. So in previously, I explained about the formation of boundary layer, and I also explained that boundary layer also has laminar and turbulent. So you could see here we have a laminar and turbulent here. So the idea of laminar and turbulent is remain the same with the definition in flow in pipes. So means in laminar boundary layer, we found that you should agree that the molecule here, okay, the velocity distribution is occur in quite in smooth streamline. So however, so when the plate here become longer and longer, so means when the molecule of fluid here travel uh, longer, so the condition of each molecule here is become not stable. So and then it start to flow unpredictable like this. So at this moment we call this is the turbulent boundary layer. So and then because the phenomenon is not is occur gradually, so means we could say that there are one region called the transition region here, means a region where the laminar and boundary is mixed together. So means a few part or some of the molecule is still flow linearly, flow smoothly, but some of the molecule will move unpredictable like this. Okay, so means that if the question asks you to draw about the laminar and turbulent, so I hope you could draw the transition here. Okay, you should draw the transition region there. Okay, so and then in our lecture here, so we divide into three conditions of boundary layer. One is the fully laminar boundary layer that we learned last week. So in laminar boundary layer, so in our syllabus, we have 6 velocity distribution. So it is by the power of 1, okay, power equal to 1, equal to 2, 3, 4, and then we have a sinusoidal, mean the sign, and also the Blasius. Okay, so this is the 6 velocity profile that you need to study. At least you could use all these velocity profile to calculate the delta star over delta, the theta over delta, and then you could use the idea of von Karman, and then you could derive the equation for delta, the equation of C small d, mean the local drag coefficient, and also the total drag coefficient. So and then please bear in mind that the Blasius here, so it has special method. Okay, so you need to solve the Blasius exact solution by using the table and do the calculation that I show in my lecture previously. Okay, all that we learned last week is actually for laminar boundary layer. So and then if the boundary layer is 100% turbulent, so if we have condition like this, a fully turbulent boundary layer, so it has another method for solving that problem. So now we will see about the turbulent boundary layer like this one. Okay, so means that you need to alert with the word fully here. So last week lecture, we are focused on fully laminar boundary layer. So we assume that all the boundary layer is in laminar condition. Now we will try to solve boundary layer which is 100% or fully turbulent boundary layers. Okay, later on, we try to solve the third condition here where they are mixing. So means we try to think about what happened, how to solve a condition where there is laminar boundary layer and also the turbulent boundary layer. Okay, so we have, I hope you could understand the situation. So now we are focusing on the fully turbulent boundary layer. Okay, so for again, I make a reminder here for laminar boundary layer. The velocity is like this. So we have a power 1, power of 2, or parabolic profile. So we have by the power of 3, power of 4, and sinusoidal. So this is again only, this velocity profile is only for laminar boundary layer. Okay, so for turbulent boundary layer, so we have two methods. So first method is power law form, and it is easier, but it is less accurate compared to method number 2. Okay, so for method number 2, we call it as empirical form, and it is more complicated, but it is more accurate compared to method number 1. So for this, actually, you could assume that, say, but the power law form is actually, we try to solve the boundary, the turbulent boundary layer by using equation. So we give you the equation for velocity profile, and then you do the integral, and finally you will get the answer. However, for method number 2, it is actually the idea of Blasius method. So in laminar boundary layer, so Blasius solve boundary layer problem by using tables. So means that they derive the condition by using the Navier-Stokes equation, okay, and then they try. We will give values. We get another value after that. Give value means you plot if x equal 1, equal 2, equal 3, equal 4, and so on. So you calculate the value for each molecule, and then you plot a graph. So after you plot a graph, you try to get equation to solving the value of delta and CD. Okay, so this is the idea of empirical form. So we will learn both, but please focus on this topic. Please focus on how to solve turbulent boundary layer by using power law form, because it is suitable for final exam, for your final exam, because it can be solved on paper by hand, by calculation. Because for empirical form, at least you must know the method. Okay, you could do if all the data are being supplied in the question. But normally empirical form is used for experimental works, because you need to depend your answer from your experimental works. Okay, so we start the fully turbulent boundary layer. So we assume, what is the meaning of fully turbulent boundary layer? So we assume that from the x equal to 0, mean from the beginning, the laminar, the boundary layer here is in turbulent condition. So turbulent condition means the velocity is unpredictable. So mean the molecule can move around like this, can go straight and cross each other, and so on. So this is the definition of turbulent boundary layer. So, and then you must know that in turbulent boundary layer, so this is the basic idea they already used in laminar boundary layer. So we have a flat plate like this, and this is the boundary layer. So this is the velocity profile that occur in the boundary layer. So again, we could calculate the Reynolds number by using the idea of rho ux over mu, or rho ux and rho ul over mu. So the L here is actually reflect the length of the plate. So this is 0, and this is the maximum, the length, which is an L. So, and then the meaning of the definition of this one is actually the rho is the density of moving fluid. capital U here is the free stream velocity, and the X is the length of the flat plate, and the mu is the dynamic viscosity of fluid. So please bear in mind that we have two types of viscosity. One is dynamic and one is kinematic. So normally we could say, we could write this mu is equal to rho nu. So mu is dynamic, rho is density, and nu here is kinematic viscosity. Okay, so in this method, okay, we assume the velocity distribution inside the turbulent boundary layer by using this form. So we assume that u over u is equal y over delta by the power of 1 over n. So means that for turbulent boundary layer, you will not have any extra equation like plus blah 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 or plus blah blah blah. So this is you could check yourself whether your answer is correct or not if your velocity profile for turbulent boundary layer has some additional terms like this. So in turbulent boundary layer, so we assume that the velocity profile is given in this form. Okay, because the power here, okay, the power here is 1 over n. So n here is an integer. So it can be 1, 2, 3, 4, 5, and so on. So it is actually unlimited, but normally, okay, normally in our syllabus, we are using these numbers because, you know, normally in normal application, except for aeronautics, so we are not talking about the aeroplane and so on. For okay, just a car moving on the road and so on and so forth. So this value of Reynolds number is the common Reynolds number that can represent the real situation. Because when you go for aeronautics, so the aeroplane, the jet fighter is moving too fast. So the compressibility effects comes in, then the idea of boundary layer need to be changed. So it needs to be considered. The compressibility effect need to be considered in your boundary layer calculation. So that's why, because in this chapter we are focusing only to calculate the turbulent boundary layer, so we need to at least to limit our range of Reynolds number. So normally in our syllabus we are using this number. However, it can be in term of to test your capability in solving the mathematical equation. Sometimes we give you the n equal to 10 and n equal to 11. However, the mathematical step is remain the same. Okay. Okay, so again, I would like to mention here. So for turbulent boundary layer, our velocity distribution need to be given like this. So u over u is equal y over delta by the power of 1 over n. So, and then to determine the value of n here, it is depend on Reynolds number. As you could see here, so if the Reynolds number from 5 times 10 to the power of 5 here until 10 to the power of 7 is n equal to 7. And then for this range, so we take n equal to 8, and for this range, we take n equal to 9. So it is good for you to remember this, range. Okay, so what is 5 times 10 to the power of 5 here? So as we know that turbulent boundary layer is only occur after laminar boundary layer. So please refer to this diagram as you could see. So the laminar boundary layer occur first. It must be start with laminar boundary layer, and then it comes into transition region, means so the percentage of turbulent is become bigger and bigger, and finally so the molecule is 100% turbulent, means fully turbulent. So now it is turbulent here. So 5 times 10 to the power of 5, it is actually the the transition borderline. So normally we take 5 times 10 to the power of 5. So we assume that from that numbers, from that limits, more than 50% of the molecule is actually changed into turbulent condition. Okay, that is the common practice or the general idea why we take 5 times 10 to the power of 5. However, if you read textbook, you will find that some textbook will give you a little bit different numbers. Sometimes they will give you 3 times 10 to the power of 5, and sometimes they will give you 1 times 10 to the power of 6, and so on. Because boundary layer is actually affected by many factors. One of them is maybe the surface roughness of the plate. Okay, so and then it will, because you know the molecule will stick on the surface. So if your surface is quite smooth, so maybe so the molecule here cannot attach very well. So means that it will change the behavior of the boundary layer. Okay, however, in our syllabus, it is okay for you to take 5 times 10 to the power of 5 as the boundary between the laminar boundary layer and the turbulent boundary layer. So please remember these numbers, 5 times 10 to the power of 5. And then, okay, you already know to solve laminar boundary layer using von Karman equation. And then in turbulent boundary layer, we will solve problems using von Karman equation. However, in laminar boundary layer, we are using Newton's law of viscosity. We do tau is equal du dy at y equal to 0. But this is a very, very important things. Please remember that in turbulent boundary layer, we are not using this equation. We cannot use this equation. So the idea is simple, because if we substitute the value, let's say we use the value of u over u, y over delta to the power of 1 over 7. So if we differentiate it with a du dy, we could get the terms here. But if we substitute the value of y equal to 0 here, so the value of du dy is equal to 0. So means that here, your calculation is correct. There is nothing wrong with your derivation, with your differential calculation. Yes, you are correct, but when you say that du dy is equal to 0, so means that the value of shear stress here is equal to 0. So it's contradict the idea of the formation of boundary layer. So we know that boundary layer is formed because the existence of viscosity. So mean the shear stress help in formation of boundary layer. So if the shear stress is equal to 0, by right, we don't have boundary layer. Boundary layer not occur. So this is actually contradict with the real condition. Because of this value is not representing the real situation. So we cannot use this equation to solve turbulent boundary layer. So I hope please do not use this equation. So it is because it is not because your calculation is incorrect. It is because it is not reflect the real situation. So the calculation is correct, but it cannot be used. Okay, please remember this one. In turbulent boundary layer, we are not using Newton law of viscosity. So this is very important. Okay, from here, I think you have one big question mark, because if we neglect or if we eliminate the usage of Newton's law of viscosity, means we cannot solve the problem of shear stress because we only have one equation of shear stress from the von Karman equation only. So actually, what we could do is we could calculate the shear stress based on numerical or based on Blasius calculation. Okay, because the Blasius calculation is quite complicated. Okay, it's complicated. You need to start with the Navier-Stokes. You need to substitute with so many variables. You need to create your own table and so on and so forth. So normally in our syllabus, we will give you the value of shear stress based on the Blasius calculation. So means that you need to compare your calculation from von Karman equation with the given shear stress here. Okay, it will be given in your question. Okay, don't worry about this. So the first thing that you need to remember is you need to know to what value you need to compare your von Karman calculation. Okay. Okay, so normally, okay, for it, but okay, the value of shear stress here will be different from one situation to another. So means that, for example, for u over u equal to y over delta to the power of 1 over 7. So their shear stress normally will given with this value. So, but for the power of 1 over 8 and 1 over 9, so the value of shear stress may be different. So mean it is worth for you to remember this one, but please make sure that you will use the given shear stress. Okay, sometimes we will give you 0.0224 or 0.0221, depend on the value of velocity profile. Okay, so how to solve this problem? So, okay, we see the question here. So we know that the velocity profile for turbulent is given like this one. So you have with the velocity profile, and then we need to solve by using von Karman equation. Then we need to equalize with the value of shear stress that given in the question. So this value of shear stress is actually comes from the Blasius calculation or the numerical calculation. So why sometimes people say it's a Blasius calculation because Blasius are leading in this was lead the calculation was among the pioneer of this type of calculation for boundary layer. Okay, so first we need to calculate what is the boundary layer thickness for that velocity profile. So mean for this velocity profile. So first we know that this is the von Karman equation. Tau is equal rho u square d theta dx. And then we need to substitute the value of theta here. So and then you are familiar with this. So this is the equation for theta. And then we substitute the value of u over u here with what we have here. Mean y over delta to the power of 1 over 7. And you could do this at home. And finally, inshallah, you will get the 7 over 72 delta. And what you need to do is you substitute into this theta. You could solve all of these. Means you can rearrange a little bit. Then you will get this term. So mean tau is now equal to rho u square d dx 7 over 72 delta. You arrange it a little bit, okay? So you just bring the delta here, coupled with the different terms here. So you have d delta over dx. So again, I mentioned here, you cannot use the idea of this one, the idea of Newton's law of viscosity, because the value of tau here is equal to 0. So it will ruin your calculation. But what you need to use is the shear stress given by the Blasius. Okay, the Blasius solution will give you the value of shear stress. in our syllabus, we will give you the value of shear stress in the question. Okay, no worry about that. Okay, let's say from the question or from the Blasius calculation, we get the value of shear stress is like this. So what we need to do is we equalize these two value of shear stress. One is from von Karman and another one is from the Blasius calculation. Okay, starting from this point, you could solve this problem exactly same with the laminar boundary layer. So what we need to do is we need to determine the value of delta. So what we need to do is we bring everything from the left side here to the right side. Okay, now we have d delta dx 7 over 72. We also will bring this to the right hand side, and then we bring the delta here, the delta to the left side. So and then we could get delta to the power of 1 over 4 d delta. We bring dx here to the right side, and then we have dx here. So I hope you could practice this at home. Okay, why we grouping the value of delta here? Because our purpose is to get the value of delta. So that's why we put all the delta in one side. So we put the delta in the left side. And then we know that this term is actually not complete because it has the differential form here. So we have d delta dx. So what we need to do is we integral both sides. So and then when we integral both sides, okay, it's will become like this one. And then when you integral it, so the constant of integration will comes up. So this is a very important step. So you need to prove whether the value of C here, it has number or it's equal to 0. So again, we substitute the boundary condition here. So at x equal to 0, the delta is equal to 0, then the value of C will become 0. So finally, we could write down this equation into this. Okay, so what is this boundary condition? You could imagine by having this flat plate. Okay, you could draw the boundary layer there, and then you could see that at x equal to 0 here at the beginning, so the formation of boundary layer is not occur yet. So means that at x equal to 0, the boundary layer thickness is still equal to 0. So we substitute this value, we could prove that the value of C is equal to 0. So and then similar with laminar boundary layer, so we cannot let this equation like this, so we need to simplify it. So we bring everything that not related, so we need to come with the delta only. We need to remain the delta only, so we bring 4 over 5 so to the right side. So you will we will have this one, and then we need to do something. So we square root with 4 over 5 here. So and then this is also need to be square root of 4 over 5. So and then you will get value of this one. Okay, so however, you need to change your equation to get your final marks in terms of Reynolds number. So means finally, we could change this term into this one. So the trick to do this is, we know that Reynolds number is rho u x over mu. And then you could see here, so it is rho u only. So to do this means that you need to multiply with an x with 1. So here you could write like this. So you have mu rho u, and then you multiply with x over x means multiply with 1. So nothing changed by the power of 1 over 5, and you have x over 4 over 5. So Now, if you have a rho u x and mu, so it will become Reynolds number. Okay, so you could, I think you already done this at home. You have idea to change this term into the Reynolds number. And then the final answer for this one is the value of delta for u over u y over delta 1 over 7 here is equal to 0.3721x over Reynolds number to the power of 1 over 5. So this is the final answer for the delta. Okay, and then we go for the displacement thickness. So we know this is the velocity profile. So this is the equation for delta star. So we get 1 over 8 delta. We substitute the value of delta, and finally we could say that delta star is equal to 0.0465x over Reynolds number to the power of 1 over 5. So next, we calculate the momentum thickness. So previously, we calculate the delta is equal 7 over 72 delta. We substitute the delta, and finally, you will get this one, 0.0368 over Reynolds number to the power of 1 over 5. So please try to do this at home. So, and then we need to calculate the shear stress. So again, please bear in mind that we cannot use the value to solve this problem. We cannot use the value from the von Karman, because the von Karman, so it will become tau is equal rho u square d theta dx. So the term of d theta dx here, okay, shows that this equation is actually not finished yet. So it's still in terms of differential form. So we cannot solve it. So you may use this equation if you solve this term. Okay. So but it takes time. So normally I propose to students, please straight away use the value of shear stress that given in the question. So this value shear stress, it doesn't have any differential form and so on. So means that this value, this equation is actually is now perfect. So let's say the shear stress is given in the question is like this. So because we have the value of delta here, so we substitute the value of delta from what we get previously. So we could say that the shear stress here is now can be written as this one, 0.0289 rho u square over Reynolds number to the power of 1 over 5. So please try to substitute this value, and please make sure that you could change the answer to this one. So this is the final answer that will give you final marks, because the term with a Reynolds number. Okay, now we are going to calculate the drag force. So this is the equation for drag force. I already explained it in previous notes. So we substitute the value of shear stress here inside this value, and then you will have this term. So this is actually after you integrate this from 0 to L. So and then what you need to do is, okay, you could refer my previous notes, or please do not worry, because this integral is actually integral to dx. So means that you need just to expand the value of x in Reynolds number. So we know that Reynolds number is equal to rho u x over mu. So you just substitute this into the Reynolds number. But please do not forget the 1 over 5. So mean total of this Reynolds number, so the power is 1 over 5. Okay, so means that the integration here is only occur for x only. So all the parameter will be constant. So you could bring it outside actually. You just need to integrate the x only. So after you integrate that, okay, you need to once again change the Reynolds number. Please make sure that the answer is in Reynolds number terms. So you will get this value. So and then we could calculate the drag coefficient. So this the drag coefficient. So this is the equation. So we substitute the value of FD here. So and then with what we have in previous calculation. So and then we could cancel off everything here. So and then we could have the final answer for the drag coefficient here is 0.0722 over Reynolds number to the power of 1 over 5. Okay, you may also calculate the CD here by using 2 theta over L. So if you see here, so the value of theta from here, you could get 0.036. So if you times 2, 0.072. So means that your CD here is 0.072. So I get this one because I put the a little bit accurate. The decimal number is there, so the answer is 0.0722. So but if you use this answer, okay, you will get it is equal 0.072 only, but it still give you a full box. Okay. So means that here you could know that you have two methods to calculate the CD. Whether you are using the drag force divided by 1 over 2 rho u square BL, or you are using the idea of CD is equal to 2 theta over L. And theta here, you need to calculate by using the equation of theta. So we have the theta is equal integration of u over u, 1 minus u over u dy. Okay, please also bear in mind, okay, please check my previous videos that sometimes people will give you in term of eta. Okay, might be it can give you that eta is equal to y over delta, and then you need to change with u over u is equal to f eta here. Okay, so when the question use this term, okay, please make sure that you could convert this equation, this theta equation, and also the delta star equation in terms of eta, because it's slightly different.